So starting with a daily dose of motivation, with the new day comes new strength and new thoughts. With the new day comes new strength and new thoughts. Problems are not stop signs, they are guidelines. Problems are not stop signs, they are guidelines. So hello friends, how are you? I hope you all will be fine, and you all might be enjoying my lectures. So today is my third lecture, and I will be continuing the remaining topic, that is special types of verniers. So in the last lecture we studied about primary classification of verniers, that was retrograde vernier and direct vernier. Now here are some special types of verniers. First, and they are double vernier, double folded vernier, extended vernier. Now coming to double vernier. See, in this type of vernier, graduations on the main scale are numbered in both the directions. A double vernier extends in both the directions with the index mark in the center. Moreover, 10 divisions of vernier is equal to 9 divisions of main scale. And if we calculate the least count, it comes to be 0.1 by 10, that is 0.01 meter. So the least count of a double vernier is 0.01 meter. And the point to be noted is that 10 divisions of vernier are equal to 9 divisions of main scale. See, this is the main scale. If this is the main scale and this is the vernier scale, so if you see this, if you see the main scale, the graduations are written in two directions. On top it is from left to right, and on bottom it is from right to left. And on vernier scale, the readings are written on both sides, on right and on left. So this is the example of a double vernier. Now coming to double folded vernier. It is also a special type of double vernier whose total length is half the combined length of the corresponding double vernier. So it is used when it is required to keep the length of vernier short to economize the space. So in this case, 20 divisions of vernier scale R is equal to 19 divisions of main scale, and least count comes out to be 0.005 meter. See, if you see the diagram, this is the main scale and this is vernier scale. This is also similar to double vernier, but the thing is that on vernier scale you can see two types of readings, on top and bottom. See, if you want to calculate the reading from left to right, if you see the coinciding division this is the 0. So from left to right you can say main scale reading is 4.2, and the second division of vernier scale, this one, coincides with it. So the final answer comes to be 4.220, and if we start from right to left, the answer comes to be 5.780. So this is the example of double fold vernier. Now coming to extended vernier. See, now remember, this is also an important type of vernier. What's the speciality in this type of vernier is that n divisions of vernier scale are equal in length to 2n minus 1 divisions of main scale. So this 2n minus 1 term should be remembered. So on calculating and equating nv equal to 2n minus 1d, v equal to 2n minus 1 upon n into d, and we know the least count is 2s minus v. So see, in all types of verniers, the formula for least count is same, s by n, or you can say d by n, whatever we are using. In this case of in this type of vernier, 6 divisions of vernier are equal to 11 divisions of main scale. So from this diagram you can see that this is the main scale and this is vernier scale. So these are the markings on main scale and these are markings on vernier scale. You can see that 6 divisions of vernier, 1, 2, 3, 4, 5, 6 are equivalent to 11 divisions of main scale. So this is the main point to be noted. So this was all about types of verniers, special types of verniers. Now we are moving on to a new and next topic, that is accuracy and precision. See, now what is accuracy and what is precision? See, accuracy is degree of perfectness in reaching an intended target. And what is that intended target? Or true values of measurements. So degree of perfectness in reaching, or you can say degree of perfectness obtained in an intended target, for an intended target, is called accuracy. And what is precision? This is degree of perfection used in instruments. Degree of perfection used in instruments and the methods of observation and calculation. So this is the basic difference between accuracy and precision. Now here are some also other terms like true error. True error is simply the difference between true value of a quantity and the measured value of a quantity. So this is called true error. So in brackets it's written in terms of formula, true error is equal to true value minus measured value. Now coming to next definition, that is discrepancy. Discrepancy is simply difference between two measured values of some quantity. See, if there is only a single quantity and the measured values are different, come to be different. So this difference in the measured values of a single quantity is called discrepancy. Now here comes another term which is related to error, that is correction. Correction is minus times true error, or you can say correction is negative of error. So on using this formula, in this above formula, we get correction equal to measured value minus true value. So this is all about accuracy and precision. See, actually we have started a new chapter, errors, accuracy and errors. So I hope you will enjoy this chapter because it's very interesting and very important also from GATE or ESE point of view or SSC JE point of view. Now we'll come to sources of errors. Now see, errors, the sources of errors can be different. For example, it can be from instrument, or it can be a personal, or can be from nature. See, if we talk about instrument, so error comes due to faulty instrument. If the instrument is faulty, then there will be error. So in personal type of error, if we are taking wrong reading or we are writing wrong measurements, then there will be error. And as far as nature is concerned, see, due to change in temperature, humidity, refraction, local attraction, magnetic declination, a lot of survey instruments or other instruments get changed and their readings get deviated. So these were the different sources of errors. Now we'll move on to kinds of errors. So there are basically three kinds of errors. First one is simply called as mistake. So mistakes, what are mistakes? Everyone knows what is mistake. Human errors due to less knowledge, carelessness, confusion or inexperience. So these come under mistakes. Now coming to systematic error or systemic error, this is also called as cumulative error. See, errors which follow a well-defined pattern are classified as systematic errors. They can be determined by mathematical expressions. These types of errors can be positive when if they make result too great, and can be negative if they make result too small. These are called cumulative error because they accumulate at the end. They add up and finally accumulate at the end. Now third type of error is, or kind of error is, accidental error. It is also called compensating error. See, these errors cannot be prevented even with sufficient care. These errors have to occur, will occur. These errors can't be prevented. So accidental errors can be positive or negative. The main point to be noted here is that they are probabilistic in nature and not deterministic. See, the example of this type of accidental error is marking the end of a chain length is common example of this type of error. So these were the different sources of errors, different kinds of errors. Now we will move on to the next topic, and one of the interesting topics, that is theory of probability. That is most probable value of accidental errors. Though we know that accidental errors are unpredictable, so following features of these errors are observed. Positive and negative errors will occur with equal frequency. Small errors occur more frequently, and very large errors do not occur. Now we'll be talking about two types of definitions. First is true value, another is most probable value. What is true value? As the name suggests, it is the exact value of a quantity, which is almost impossible to measure. No instrument can measure the exact value of a quantity. Now coming to second definition, most probable value. It is the value of measurement whose chances of being correct are more than the other measurements. So this is the type, this is known as most probable value. Now, before starting the next definition of most probable value, I will be talking about the normal distribution of errors. If we talk about the normal distribution, a graph is plotted between frequency and error, and this graph follows normal distribution, and we can see a lot of intervals here. This is actually 1, 2, 3, 1, 2, 3. Here we have seen that what is most probable error. The most probable error is defined as that error for which there are equal chances that the true value will be less than the probable error or will be more than the probable error. In other words, the probability of true error being less than the probable error is 50%, and the probability of true error being greater than the probable error is also 50%. So if we from this graph, if this is 0.5 or 50%, then this interval comes to be from I will make here, this is minus 0.6745 sigma, and this is plus 0.6745 sigma. So this is the confidence interval for most probable error. See, the theory of errors or theory of probability, first of all you have to remember that it follows normal distribution, and all of us are aware what normal distribution is. Now coming to the principle of least squares, this is another definition of most probable value. See, as per the principle of least square, the most probable value is one for which the sum of the squares of errors of a set of observations is least. What is he saying? The most probable value is the one for which the sum of the squares of errors of the set of observations is least. Now, if n be the number of observations to a quantity, then standard deviation sigma can be written as sigma is equal to plus minus under root summation v whole square upon n minus 1, where v is difference between any single observation and the mean of the series. That is, you can say x minus x bar. Or summation v square is equal to summation x minus x bar whole square. So this is the formula for standard deviation. Now we will see some of formulas. Like the first one is probable error of single observation. Probable error of single observation. So this is the same one that I discussed you before, whose confidence interval was this one, minus 0.6745 sigma to plus 0.6745 sigma. So this confidence interval is for probable error of single observation. So as from the normal distribution, the formula comes out to be ES, that is probable error in single observation, equal to plus minus 0.6745 sigma. Why plus minus? Because it shows the confidence interval. Now we know the value of sigma. The value of sigma is under root summation v square by n minus 1, where summation v square is simply summation x minus x bar whole square. So this is probable error of single observation. Now the second formula is most probable error of the mean. So this formula is related with probable error of single observation. So from the formula you can see EM, that is most probable error of mean, is equal to plus minus 0.6745 sigma by under root n. So this new term comes here, or on substituting the value of sigma we get plus minus 0.6745 under root summation v square upon n into n minus 1. Or you can simply write as most probable error from mean is equal to probable error of single observation upon under root n. Now third formula is maximum error. So this is simply as plus minus 3.29 sigma. Now here comes an interesting topic: errors in terms of significant figures. See, you know significant figures? If I write the term 4.3864, can any one of you tell how many significant figures are there in this number? So this number has, this has 5 significant figures. So on the basis of this concept, we have some examples, and if you are given a number with decimals, you can directly calculate its maximum error and probable error. See, for example, we are given the term 4.6 and we have to calculate its maximum error and probable error. So how can you calculate? See, we have to see after decimal how many digits are there. So after for example here after decimal there is only one digit. So in maximum error we have to use 0.05. That means in case of maximum error you have to increase one more decimal place and write here on the first place you have to write 5. And probable error is simply by dividing maximum error by 2. So probable error. Similarly, in second example, the question is 5.86. So its maximum error will be, see after decimal here are 2 points or 2 digits. So in case of maximum error there will be 3, and only on first place there will be the value will be 5. So on dividing it by 2 we get 0.0025. that is our probable error. So these are also some types of questions. Now we will try to solve some of the numericals that are very important. See, the first numerical says an angle is measured with a standard deviation of plus minus 2. And he says calculate the most probable error. Also determine 95% error and the maximum error. The formula for most probable error, if I denote it by MPE, it is simply given as 0.6745 sigma. So we are given the value of sigma, so we can simply calculate it as 0.6745 into sigma is 2. So the answer is 49. 95% error. See, we have to calculate 95% error. For that, we need to remember a table for different percentage errors. See, I'll make it here. For 90% error, E90 you can say. For 90% error, there will be for the error will be plus minus 1.645 sigma. For 95% error, there will be for 95% the error will be plus minus 1.96 sigma. For 95.5% error, it will be plus minus 2 sigma. And for 95% error, the value comes to be 1.96 sigma, and for 95.5% error, value is 2.6 sigma plus minus, and for 99.7% it is plus minus 3 sigma. So in our question we have 95% error, we have to calculate 95% error. So here the answer will be plus minus 1.96 sigma. So on substituting the values, we get sigma is 2, so we get 3.92 plus minus 3.92. And similarly, maximum error is represented by E of 99.9%, and its formula is, as I told you, plus minus 3.29 sigma. Upon substituting the values, we get plus minus 6.58. These are all minutes. Now the second question says a distance is measured a large number of times and its 90% error is plus minus 0.822 centimeter. What is the standard deviation? What is the percentage error for plus minus 1.5 centimeter? See, he's saying 90% error, and from this table we know E90% is how much? Plus minus 1.645 sigma. And E90 he has given as plus minus 0.8225. So on substituting we get plus minus 0.8225 equal to plus minus 1.645 sigma. So on solving we get standard deviation sigma as plus minus 0.50 centimeter. It is in centimeters. So we have calculated the first part. He is saying what is the percentage error for plus minus 1.50 centimeter. See, we know he is saying plus minus 1.5 centimeter. See, if sigma is 0.5, then if we multiply sigma by 3, that is 3 sigma, it comes out to be 1.5 centimeter plus minus. That means it corresponds to 3 sigma. So from this table, 3 sigma corresponds to 99.7% error. So required percentage is 99.7%. So this was all about this numerical. Now we will solve a few, not more questions, only 2 questions from previous year's GATE and ESE. Hope you will like these numericals and you will be enjoying all of this. The first question says, it was in ESE 1996. The number of observations required of an operation to produce results having a specified accuracy. Remember, first portion, it varies inversely with the square of confidence interval. Secondly, varies directly with the square of confidence interval. Third one is saying increases with the possible magnitude of the average expected value. Or last portion is saying increases with the range of observed values, namely the difference between the maximum and the minimum values of the observation. See how to solve this type of question. He's saying number of observations required of an operation to produce results having a specified accuracy. See, he's simply telling us to use a formula for single observation, error due to single observation. We know the formula is plus minus 0.6745 root of summation v square by n minus 1. See, from here we will calculate the value of n. So upon squaring both sides, we get n minus 1 equal to 0.6745 by ES whole square into summation v square. Or we can get n equal to 0.6745 by ES whole square summation v square plus 1. So from this diagram, from this expression, we can clearly say that these are number of observations and this ES is the confidence interval. So option A will be correct, that it varies inversely with the square of confidence interval. This is square now. So that's all about this question. Now coming to second question. See, this question came in ESE 1996. Now coming to second question, this also came in ESE. The question says, this is regarding Verniers. It's an interesting question. If you have understood all types of Verniers, then you will be able to answer this very easily. The question says, which of the following statements is correct? First is, in a retrograde vernier, n-1 divisions on the primary scale are divided into n-1 divisions on vernier scale. So, as all of you know that this can't be right, so this one is wrong. A double vernier consists of two simple verniers placed end to end, forming one scale with 0 in the center. Yes, it can be correct. Third one is, in an extended vernier, 2n-1 primary divisions are divided into n divisions on the vernier. As we already studied that in an extended vernier, 2n-1 primary divisions are divided into n divisions. So 2n plus 1, it's again wrong. Third is, in a direct vernier, n plus 1 primary divisions are divided into n equal divisions. It's absolutely wrong, as n-1 primary divisions are divided into n equal divisions. So the answer goes with option B, that is, a double vernier consists of two simple verniers placed end to end, forming one scale with 0 in the center. So that was all about today's lecture. In further lectures, we will be discussing about weights, laws of weights, other questions related to accuracy and errors, and after that we will simply start the next third chapter, that is linear measurements. So that's all for today. Hope you have liked this lecture today. So if you have liked the lecture, then please like the video and subscribe the video. So that's all for today. Goodbye.